This is my first video in my module on calculating the mean or the average for a probability distribution. Okay, and we're going to start by kind of discussing what finding a mean for a probability distribution even really kind of is articulating to us. So we're going to start by considering a thought experiment in which we flip two coins. What I want to figure out is this: on average, what will be the average number of heads that I will see when I flip these two coins? So the first thing we're going to do is actually list out the sample space, which actually happens to consist of these four possibilities. We could certainly get a heads and then a heads. We could get a tails and then a tails. We could get a heads on the first coin, tails on the second, or a tails and then a heads. But we say these are the four possibilities that could occur with my coin. So for instance, if we're talking about calculating a mean for a probability distribution, I suppose we should construct a probability distribution. So probability distributions, remember, look like this. We've got a kind of a t-chart sideways. But we say, first of all, let's let our variable equal something here. We let x equal the number of heads that we get on a single outcome here. So we look up at the four outcomes we see here, but x represents the number of heads that we get when we flip those two coins. And then down here we just write the probability that that actually occurs. So in terms of this particular experiment, we say, well, how many heads could you get when you flip two coins? And of course we could either get 0, we could get 1, or we could get 2. And down here we're just going to calculate the likelihood of these things actually happening. So for instance, we say, well, how many of these four over here had no heads in them? And we had one of them. It was this one with 2 tails. So we get the probability of this occurring is a 1 in 4 chance. We say one head, exactly one head. We had actually two of these. This one had one head in it, and this one had one head in it. So we say it's a 2 in 4 chance here. And anybody who's savvy with probability distribution should know that this last one has to come out to be 1/4, because of course all of these probabilities of everything in the sample space have to add up to 100% of our stuff. But sure, two heads, we said we had two heads occur in this outcome here. So when we talk about what is the average number of heads, let's say we're playing a game in which we flip these two coins, and the way you win this game is necessarily, say, you have at least one head on the coin. The question I want to answer maybe is this then: on average, if we were to flip these two coins, not once, not twice, not thrice, not 10 times, not 100 times, but if we were to flip these coins for eternity, which is impossible, by the way, and keep track of the outcomes that we see here, on average, how many heads would you expect to see occur? And remember, the average, the mean is the most typical. That's what mean means. Sorry to be redundant there, but it's the most typical. So most typically, how many heads would you expect to see? Well, when I'm looking at my table up here, and x represents the number of heads, I can see overwhelmingly it occurs, one head pops up more than anything else. It's most likely to occur. So what I'd like to do is actually set out to find the average number of heads. So what I'll have us do here is, just looking at this over here, we say, let's find the average of this. Now, to find the average, of course, we've done this before. You add everything up and you divide by however many there are. So we're going to add up the number of heads in each instance. So for instance, in the first one here, we said we had 2 heads. So we had like 2. Plus now the second instance here, we had 1 head. So we had a 1 head. We say we also had 1 head here, so 1 head there. And then down here we had no heads. So if I wanted to find the average of these 4 instances, we would add them up and divide by however many there are, which we get 4 over 4, which comes out to be 1. And I'm going to label this 1 head. So in other words, if we were to flip these coins and list out all the possible ways this could happen in our sample space, on average we would expect to see only 1 head appear. And you know what, honestly, when you look at this, it kind of makes sense. 1 head flipping 2 coins appeared more than anything, more than flipping 2 heads or flipping no heads. So we say 1 head is what I could expect. Now the interesting thing about this is considered a long-term average. That's what this is. And so in other words, what we're saying is, if we were to flip these coins for eternity, what we would instead get is saying, on average, out of all those eternal flips, what did we see for a number of heads? It's actually 1 head in the long run. So we're interested in calculating this mean. What I'm actually going to do is try to reformat this so that instead of actually having to list out the sample space every time, that is, consider if we had flipped 3 coins, that would double the size of our sample space here. We'd have like 8 possibilities, and then I'd have to go average up the number of heads. Or if I flipped 4 coins, we'd have 16 possibilities. I'd have to go average out all the heads in each 16 possibilities. Could we actually re-scribble this? And actually we can. I would like to point out that this is a monomial divisor. Mono means 1. We can actually list everything on top of the numerator, and that's sum over the 4. So in other words, we could say it's this. We could say it's a 2 over 4 plus 1 over 4 plus 1 over 4 plus 0 over 4. But another way to kind of interpret this is kind of like saying this. We got 2 heads 1/4 of the time. And we got 1 head half of the time, or 2/4 of the time. If we were to put these together, we get here 2/4. And I could say put the 2 out front, or put the 1 out front, sorry, 1 head 2/4 of the time. And then we'd say, okay, well, we got no heads 1/4 of the time. So we got no heads 1/4 of the time. The interesting thing about this is if you go over here and look at our probability distribution, we could have calculated this the same way by doing this right here. Okay, we get 2 heads 1/4 of the time. So if 1/4 of them overall are 2 heads, and half of them overall are 1, and 1/4 of them overall are 0, to find the average of this, we could just evaluate this expression right here, just as we did up here. But the benefit of looking at it this way happens to be this. I want you to notice that these 3 values right here happen to be the x values, or the different possible things that could have occurred up here in our probability distribution. And when you're looking at these values here, we say these are our probability values. Probability, probability, probability. So basically what we had done was this. We took 2 times 1/4, but the reason why is because we get 2 heads 1/4 of the time. So we would multiply these together, and it looks like we get 2/4. So we could say, well, if we were to make another row down here where we say what we're doing is taking all of our x values times p of x, we say 2 times 1/4 is 2/4. We say we took the possibility of getting 1 head 2/4 of the time times its probability. So we took this 1 right here, multiplied it by its probability. 1 times 2/4 is 2/4. Okay? And then we say this last one here, we say, well, we got the possibility of 0 heads, and that occurs 1/4 of the time. If we took 0 times 1/4, we would get 0/4. Essentially, what we've done now is, after we've taken all of these individual things that can happen times their probabilities, we need to sum them. So add them together. So that'd be these summation signs here. So what we're going to do is this. We're actually going to build in one last sum down here at the end of this row where we took all of these probabilities times their individual things that could happen. Multiply, multiply, multiply. And what we're going to do is we're going to add these up here. So we get 0/4 plus 2/4 plus 2/4 equals 4/4, which was our 1 head. Okay. So instead of actually having to write this out every time, what we'd like to do is formalize this. And essentially what we could do is we say, well, if you wanted to find the average number of, say, x, or in this case, number of heads, what we'll do is we'll go through, we'll take each thing that can happen times the likelihood that it does actually happen. Take x times the probability of x, and then we'll put these things down here and then sum them up, and that'll give us the average. Okay, so the average in this case was 1. So to formally define this, if you're keeping track here, this is a formula you're going to want to know, but we say the average. This is mu, the Greek letter mu represents the average. Sometimes we use the x bar to represent an average, but we say it is equal to the sum of this. All of our things that can happen times their respective probability. So the same thing we just did up here, we multiplied all the x's times their own probability and then added those things up, and that gives us the average here. So this is our formula for the mean of a probability distribution. So I just want to show how this is kind of put together and used in different instances. So for example, let's go on to example 1 here. We say find the mean for the number of spots. They're called pips, but the number of spots that appear when you roll a die. So let's go ahead and start with this. We say, well, our variable in this case equals the number of spots on my die, so on the die that I roll. So when we talk about the probability distribution here, we say, well, x is the number of spots, and probability of x is how likely it is that that occurs. Excuse me. We say, well, what could you roll on a die? Well, we could roll a 1, we could roll a 2, we could roll a 3, a 4, a 5, or a 6. We say all of these possibilities, if you find their probabilities, we say, well, each of these is 1 in 6 chance. Of course, 1 in 6 if you're talking about a die. But the simple fact is we said, well, what's the average number of pips that show up on the die? So just like we did prior to this, we're going to build in a third row on this table in order to find the average. And here's how this works. We say this row represents the product of everything that can happen with the probability it does. So for instance, if we fill out the rest of this table here, we get this situation. We say 1 times 1/6 is 1/6. 2 times 1/6 is 2/6. 3 times a 6 is 3/6. This will be 4/6. This will be 5/6. And this will be 6/6. So if we want to find the average now, what we need to do is sum these. So we're going to sum all of those probabilities times their respective events, And so we would say, well, the nice thing about this is it's over 6, but we say 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15, and 15 plus 6, of course, is 21. So we'd say, well, what is the average number of pips that show up on a die? Well, if everybody's equally likely to happen, and we were to keep track, if we were to roll this die for eternity, oh, I rolled a 2, a 3, a 5, a 6, a 1, and kept track of all those, and then averaged all of those outcomes out, we would get this 21/6. And as a matter of fact, if we were to reduce that, I think we get 7 halves, which is 3.5, but we'll take 21 and divide by 6 here, and we get 3.5. So we can say 3.5 pips. Now this is entirely reasonable given that 3.5, if you look at your distribution up here, 3.5, you can't even roll a 3.5. But it is right in the middle, and the reason why it's so balanced is because everybody was just as equally likely to occur as the next. Okay, so we say 3.5 pips on the die. Now I want to talk about 3.5 pips. First of all, if we were to create a probability distribution graph from this, we'd say X is the number of pips down here, and our probabilities are over here. Everybody had a 1 in 6 chance. So maybe I'll label my axis over here. We'll say this is like 3 in 6, this is 2 in 6, this is 1 in 6 chance. We say, well, we'll list all the possible outcomes down here. We said, well, 1, a 2, a 3, a 4, a 5, or 6 could happen. But when we look at this graph, we say everybody has a 1 in 6 chance of occurring. And if that's the case, we say, well, where would the average be in this data set? 3.5 is entirely reasonable to say. So the first thing I want to mention is it is the average of this entire distribution of data. And it looks like it should be the average. And the second thing is this. It's kind of like saying if you were to roll this die forever and actually keep track of what numbers pop up and then go back and average all those numbers, you should get an average roll of 3.5. So just like in certain instances with discrete things, discrete variables, like for instance, number of siblings, if the number of siblings in my family, I keep track of how many siblings different families have and I average them out, you might come up with an answer that says the average number of siblings is 3. That is, the most typical family unit has 3 siblings with you, okay? But sometimes you might get an answer like 3.28 siblings, which, of course, 3.28 siblings is not reasonable in terms of you can't have 20/100ths of a sibling along with 3 other siblings. But it does give us insight into what we're getting. So when we talk about the mean for probability distribution, it is like a long-term or eternal average for the number of things that can happen up here. Okay, so we'll look at a couple more examples in my next video. Cheers.